Hello, my name is Brian Yamas.
And my name is Jonathan Mesa, and this is our final project for ECE120 Lab.
Our project aims to create and demonstrate a four-digit random pin system. We also hope to demonstrate how to interface a keypad through scanning, debouncing, and decoding. The software scanning and debouncing through in and out ports, bit shifting, and bit testing will also be explored.
In addition to that, we hope to demonstrate how to interface with the DC motor and control its direction through the H-bridge configuration. Finally, we aim to generate a random four-digit sequence and compare with values entered through the keypad. The principal idea of our project was to incorporate the understanding of the keypad and be able to compose a program that will generate a four-digit random sequence, which will then trigger the DC motor to lock, counterclockwise rotation, or unlock, clockwise rotation. The concept of a randomized pin is an idea that has application in security. Only the user could have access to the new pin generated by the code. The project incorporates a DC motor. A DC motor is a motor which translates direct current into mechanical motion through coils and stationary magnets, which repel when the polarity of the coil is directed. Also used in this program is a keypad. The keypad works as a series of switches in which either the rows or the columns have a voltage and produce an arc, which then triggers the pick when the arc is interrupted in a certain part of the switches. The connection layout is presented on this slide.
Now, the hardware. When it comes to building the board, the project calls for a DC motor and a keypad. The keypad is connected so port B, RB0, RB1, and RB2 are used as input pins that are connected to the CV2 pins 4, 5, and 6, which are connected to the 3x4 matrix keypad. But in this case, we're only using it as a 3x3 keypad. On N4, N5, and N6 as the column of the keypad as implemented in the software. Connections are from the times 10 pins 1, 2, 3, which are RB0 to RB2, to the time 4 pins 3, 2, and 1. Then the board traces to the SV2 pins 3, 2, 1, which would represent the columns 1, 2, and 3 respectively. Port B, RB3, RB4, and RB5 from times 10 pins are used as the outputs of the CV2 pins 0, 1, and 2 to the 3x4 matrix keypad on N2, N1, and N0 as rows in the software implementation. Connections are from the time 10 pins 5, 6, and 7 to the time 4 pins 5, 6, and 7. Then the board traces the CV2 pins 5, 6, and 7, which are rows 3, 2, and 1 respectively. Now port A, RA0, RA1, and RA2, as well as RA3 from the time 8 pins are used as the outputs for the LEDs. The times 6 pins 1, 2, 3, and 4 for the binary key value indications. The actual keypad is placed on the far right of the SV2 socket that is used pins 1 through 7. Now, for the motor, we will also be putting this on port B, pins RB8 and RB7 used as output pins to the optical isolator pin times 38 pins 1, 2, 3, and 4, in which are used to drive the FETs Q3, Q4, Q5, and Q6. Then finally, this is connected to the appropriate external power source. Now, once we have all our hardware set up, this is what the final layout of the circuit with both the motor and the keypad and the LEDs connected would look like. To begin off the code, we need to initialize the port and the timer registers. Tris A is completely cleared to make them all outputs since we only use the LEDs here. In Tris B, we set 07 hex to make the bottom 3 bits inputs, while the rest should be outputs. The inputs read the column values from the keypad. The other bits are just used for RB5 through RB3 of the keypad rows, and to drive the motor, RB7 and RB6. The option register was loaded with 0F hex in order to activate the timer mode of timer 0. No prescaler was used for the timer 0.
The main program began by clearing and then setting the first software flag. This software flag was used in determining whether or not a random number should be generated during this iteration of the main loop. A bit test was used to check the software flag, as seen by the BTF-SS instruction next to the label named check. If the software flag was set, the generate subroutine was called. This subroutine will be explained later on. In addition to the software flag for generating a random number, the address location 41 hex, which is the pin equate, was used to keep track of which number in the 4-digit sequence the program was at. Its relevance and use will be noted later on as well. After bit testing the first software flag and generating a random number if necessary, the program went on to check whether or not a key was pressed on the keypad. For this reason, a second software flag called found was utilized. In addition to that, an offset was determined during the keypad check that would allow the program to know the numerical value of the key that was pressed. Both of these registers were cleared at the start of the keypad portion of the main loop.
In order to check whether a key is pressed or not, a 0 has to be applied to each row. This is of course done one at a time. This is why the program begins by checking the rows by loading different literal values into port B bits in order to isolate each row. For instance, in the first row, we load 30 hex to isolate row 1, 28 hex to isolate row 2, 18 hex to isolate row 3. After these values were loaded into port B, respectively, the check row subroutine was called. After this subroutine was called, the found flag was bit tested to check whether or not the key was pressed. If 1 was pressed, the program went to the save key subroutine and then began again at the start of the main loop. If no key was pressed during any of these row checks, the program began the main loop all over again. The generate subroutine is called whenever the first software flag called flag is set. The subroutine begins by calling the randomized subroutine and then moving this random value to port A, where the random value would be visible via the LEDs. The first software flag is then cleared and the program returns to the main loop to check the keypad.
The randomized subroutine began by sampling timer 0. This value would then be XORed with the old random value, ensuring that the new random value would not be dictated by timer 0 alone. Through a series of swap instructions, more XORs, and taking the 2's complements of some results, a second sampling of timer 0 and a final bit test of timer 0, a new value was acquired. This new value, stored in random, was generally above the range of numbers needed, which for the 3x3 keypad matrix were the numbers 1 through 9. So, the program made sure to mask everything except for the bottom 4 bits by adding the new value with hex 0f. This limited the range from 0 to f. Then the program bit tested the limited value to see if it was between A and F. If it was, the value was truncated by subtracting by 6. The next condition that needed to be checked was whether the new value was 0. Because this experiment only used a 3x3 keypad matrix, which only included numbers 1 through 9, if a 0 was generated, there would be no way for the user to input a 0 from the keypad. Thus, literal 00 was IOR'd with random in order to not corrupt the generated random value. This also allowed the program to check the Z flag in status to determine whether random was 0. If the Z flag was set, the randomized subroutine was called again. Otherwise, the generated value was definitely between 1 and 9.
Now returning to the keypad instructions, the check row subroutine was used to go through a row from the keypad to determine if the key was pressed. This was done by storing port B into temporary location. Using a loop that went 3 times, once for each column in a row, right shifting the input bits, then bit testing for the carry flag. If the carry flag was set, that meant that no key has been pressed. Therefore, the offset value was incremented. The loop counter was decremented and tested for 0 in order to know if the program needed to continue bit testing. If the carry flag was found not to be set, that meant the key had been pressed in that row. This then took the program into the save subroutine.
The purpose of the save subroutine was to set the second software flag to indicate that a key had been pressed. This was done by complementing the found value. In addition to setting the found flag, the save subroutine also continued by doing a software debounce. The software debounce did almost the same thing as the check row subroutine, except that an outer loop was added. This outer loop was used to debounce several times in order to assure a clean read of the input. If no key was found during the 64 iterations of the debounce subroutine, the program returned to the main loop where the found flag was tested, which caused the program to enter into the save key subroutine.
The save key subroutine began by incrementing offset, because the offset value acquired via the check row subroutine was off by 1. For example, pressing 1 on the keypad would produce a value of 00 hex. Pressing 2 would produce a value of 01 hex. After updating the offset, the value is then XORed with the value stored in random. This allowed the program to check the Z flag in the status to determine whether or not the key press matched the current digit in the pin sequence. If the Z flag was set, the program entered into the continue subroutine. If it is not set, the program entered the restart subroutine.
The restart subroutine was utilized to show the user that the number that was inputted was incorrect. This was made visible by making the DC motor go counterclockwise, which was done by IORing literal 40 hex with port B, then calling a 25 millisecond delay, and then clearing RB7 and RB6. After this, the pin counter was cleared, and the first software flag was set so that the program could generate a new random number the next time it entered into the main loop.
Finally, the continue subroutine was utilized whenever the user inputted the correct pin value. First, the pin counter was incremented. After this, bit 2 was tested, because if it was set, that meant that the user had successfully entered the 4-pin numbers correctly. If bit 2 was set, the DC motor was made to spin clockwise by IORing literal value 80 hex with port B, calling a 25 millisecond delay, and then clearing RB7 and RB6. The pin counter was only cleared whenever bit 2 was set in order to start the next 4-digit sequence. Before entering into the main program, the first software flag was set. Now we're going to demonstrate the random values generated by the randomization routine. This will simply be done by just resetting the board, which would demonstrate a different value because another value would be generated.
We're ready.
So now we are going to demonstrate whether a wrong value is pressed on the keypad, the motor should turn counterclockwise. So the value there, it was wrong. Once again, wrong value entered, counterclockwise. Also demonstrated in the FETs.
Now we're going to show what happens when you get the sequence correct. As shown by the LEDs, the current number is 8. By pressing it, the motor should not move because of, as we explained in the software, it will only move clockwise when we get all 4 correct. So first one should be 8. The second number should be 8. Next number 9. And the last one was 4. And if you saw, the motor went clockwise. Again, if we go to the sequence again, this time the sequence will be 1, 5, 8, and 6. As you saw again, the motor went clockwise, indicating that we went through the four sequence correctly.